All right, you guys hear me? Nope.
Yep.
You do hear me, yes?
Yeah.
Cool. All right, we're ready to go. Last time we kind of ended on this review of basic acid theory and what acidic water and basic water. You should know this from Gen Chem. Now for organic chemistry, a big thing we're going to use is pKa values, and especially for different organic molecules, we have to kind of, what it does is it's a universal measure of acid strength for any molecule, but we really use it for organic molecules. So when we say HA, we mean an acid, right? It could be acetic acid or benzoic acid or any acid. And so what you do when you consider an acid is you imagine it would be dissolved in water, and the equilibrium that would form, well, water would take the proton, right, and give you H3O plus and A minus. And so the equilibrium is products over reactants, H3O plus times A minus divided by HA, and water. Water's a constant, factors out. So then basically Ka is going to be H3O plus over times A minus divided by HA. And what that does is it kind of measures the dissociation. And we take a negative log 10 of it, so it's pKa, becomes pKa. pKa is the pH at which half of the acid is dissociated. So pH is kind of a constant. Well, let's see, how should I say it? pKa is actually kind of dependent on a molecule. pH is kind of an experimental thing. It's like how acidic is the water, right? Is it low acid or high acid? But the big thing is what happens when pKa is the same as pH. Say my molecule has a pKa of 5. My molecule has a pKa of 5, and if the pH is 5, at that point, half of the molecule is dissociated and half the molecule is undissociated or associated. And so a lower pKa is stronger acid. That's the big takeaway here. Let's look at a couple acids going from crazy acidic to crazy non-acidic. So HI, hydrogen iodide, is probably one of the strongest acids known. The pKa is negative 10. And remember, low number is more acidic. And then we have like the opposite extreme is methane, or like alkanes. Methane is a pKa of 50. So it's basically like at that, you can't have a pH of 50, right? So, but big thing though is methane is never, or alkanes, you say ethane or propane, are never going to give up their proton. It's just so non-acidic that it just doesn't dissociate. These other ones though, like hydrogen bromide, chloride, sulfuric acid, hydronium, nitric acid. Yeah, these are all fairly acidic. What's the first? Well, I will say probably the organic molecule you might be the most familiar with would be acetic acid, probably. pKa is kind of in the 4 to 5 range. And then like alcohols are around 16. You don't have to memorize these, but you will see them all the time, and you'll kind of get a handle of what the pKa of an organic molecule is. And I'll probably ask you in class. I'm not gonna, well, I don't want to say what I'm going to do in the quizzes yet, but the quizzes are yet to come. I'll give you an announcement when we're getting ready for the quizzes. But it is good to have a general ballpark. I wouldn't worry too much about memorizing these. Water is roughly where methanol is also. So methanol and ethanol and water are all in the 15, 16 range, okay? Chemical structure allows us to predict the relative acid strength, or the pKa value. Chemical structure, that's really useful because now we're all experts at organic structure, right? We can understand chemical structure of organic molecules, and hopefully inorganic from Gen Chem. Relative strength of an acid increases, so more acidic, when you have more electronegativity of the conjugate base, A minus. So if we can compare, like, on the periodic table, carbon, nitrogen, oxygen, chloride, who's the most acidic? Well, as you go to the right, there's more electronegativity, and that stabilizes negative charge. So HF is the most acidic. Like carbon is the least acidic. We just saw methane, and we saw the pKa was 50, right? It's the most acidic thing on the most non-acidic thing in the universe. So as we go to the right, it gets more acidic, and that's because of stabilization of A minus. Increasing size of A minus will also increase acidity. So as you go down on the right side of the periodic table, I realize that, usually I teach in a big lecture hall and we have a periodic table so you can see it, but I don't have that in my lecture notes. It might be good to have a periodic table from time to time that you can see. But yeah, as you go down the periodic table, HF, HCl, HBr, HI, you also increase the acidity. So HI we just saw is the most acidic one on that table, certainly. Large atoms have mismatched outer shell orbitals. And so when you go down, the proton is like row 1, and then these go 1, 2, fluorides, row 2, row 3, row 4, row 5. As you go down the periodic table, they're mismatched outer shell orbitals, right? That makes sense, and that would be easier to dissociate a bond with mismatched outer shell orbitals. That's why as you go down the periodic table, things get more acidic. Make sense? All right. Let's see. Sorry, just managing my Zoom. Okay, well, anyway. I can't see the chats. So if you have a question, just speak up. I don't know what's going on in the chat for me. Okay, cool. So the other big thing, I'll say the most important thing probably for organic chemistry is resonance stabilization of A minus, right? If you have resonance stabilization of the conjugate base, that would maybe increase the acidity, right? What if you don't have resonance stabilization? You have like a conjugate base with no resonance stabilization. Would it be acidic or non-acidic? It would be non-acidic, right? And we'll show an example in a second. If you have stabilization of A minus through whatever means, it could be electronegativity, it could be the bond mismatching. If A minus is favored to form, then you have an acidic molecule. And resonance stabilization of A minus is a big way to do that.
What exactly, can you just give me an exact definition of what resonance stabilization is?
Yeah. Let's see it on the next slide. But the basic summary, first of all, we know resonance, right? Resonance is a way that we can resonate electrons, right? Maybe what I did not explain before is that when you got resonance, you got stabilization. Maybe I didn't explain that, but resonance implies stabilization. Okay, let's show an example of it. Yeah. So resonance stabilization of A minus explains acidity in a gazillion examples of acids in organic chemistry. A gazillion examples. We're going to be doing resonance stabilization of the conjugate base through the end of organic 2. Okay. All right, gazillion. Put that in your notes. Okay. So first, let's show methanol versus acetic acid. Anybody know the pKa of an alcohol? We just said it. It's about the same as water, roughly 15 or so, right? pKa is 15. Acetic acid is about 4, 5. Okay, so who's more acidic? Well, I show it. Methanol is a weaker acid. Acetic acid is a stronger acid, right? And we know that from the pKa, right? Okay, so thinking about the chemical structure, how do we rationalize why methanol is a weaker acid and why acetic acid is a stronger acid? Let me first tell you how not to do it. In a way, a lot of students are going to make this mistake, so don't be the student that makes this silly mistake. A lot of students just say, oh, it's resonance, or something about, resonance. It's not specifically resonance. What it is it's going to be resonance stabilization of the conjugate base, okay? So methanol, when water takes the proton off methanol, it becomes methyl O-, right? And H3O+. This is not a resonance stabilized conjugate base. There's no resonance. You could try and and never come up with a resonance structure of this, right? There's no resonance. Now it is a little electronegative because oxygen is a little bit electronegative. That's why the pKa is about 15, right? But there's no resonance, right? But this guy, what is the pKa of it? We said 4 or 5-ish, right? Water takes the proton. Now you have this thing that the conjugate base has resonance. So there's not only these resonance structures, you could separate the charge, like you could draw a third resonance structure with carbon plus, both oxygens are minus. Remember, that's a minor resonance structure. We don't really care about that. But these are very prominent resonance structures, right? These two resonance structures of acetate. Okay, so this is stabilized. That's what I was trying to say. Resonance stabilization of A minus explains acidity. So this is a resonance stabilized species, and what's the net effect? This has a lower pKa, 4, 5, right, versus 15. Okay. So when I ask, generally, and this goes through the end of organic too. I'm gonna ask them quizzes and stuff like, like here's methanol, here's acetic acid. What's the chemical basis for acidity? And people are going to say resonance. The answer is no, it's not resonance. It's resonance stabilization of the conjugate base, because it's the conjugate base that's being stabilized. Resonance applies to the acid too, but that's irrelevant. We don't care about the acid, we care about the conjugate base, all right? Oh yeah, just back to this. There's one thing that I would maybe recommend on my electrons for the resonance. And I've mentioned this 1,000 times already to you. Circled initial lone pair. Like if you're drawing the resonance structure, and say the arrows aren't there, first thing you do is you circle lone pair, then you tick it in and then tick it up, okay? So I recommend arrows or circles, circle the bonds, okay? Lewis acid-base theory is a more general model. So what we just were talking about was Bronsted-Lowry acid-base theory. So Lewis acids define acids as not a proton donor, proton acceptor, but rather electron donor, electron acceptor. So it's just a different way of describing essentially the same thing. Lewis acid is a species that contains an atom that is at least 2 electrons short of a closed outer shell. It's called an electron acceptor. Okay, so what are some Lewis acids? H+, which has no electrons around it. It is a Lewis acid as well as Bronsted acid, right? But these guys are not Bronsted acids, metals. The metals are not. And like borane, how many electrons are on borane? It looks like 2, 4, 6, right? Is that an octet? Is 6 an octet? 6 is not an octet. It's a, I don't know, hextet, or I don't know what you call it. But boron has a free p orbital. So it's an empty p orbital. And that can be basic, that makes it acidic. So this is actually Lewis acid. Carbon with a plus charge was called carbocation. Remember that? Carbocation. Well, it's also a Lewis acid. It's got a free p orbital. Got 6 electrons, sp2, just like this is sp2. You have the extra p orbital that can be overlapped with other electrons, right? Magnesium chloride or aluminum chloride, all these transition metal halides can be Lewis acids too. X could be other halogens, chlorine, bromine, probably those are the most common. A Lewis base is a species that contains a pair of electrons. It's an electron donor. Okay, so Bronsted acid-base theory is mostly about protons. Lewis acid-base theory is more general. It includes protons, but it also includes like metal Lewis acids. Okay. These are some Lewis bases. Hydroxide. So it's got an electron pair that can react like with one of these guys. All of these have pairs of electrons. Water. Water is a Lewis base because it's got a pair of electrons. Sulfur dihydrogen. Hydrogen sulfide. Hydrogen sulfide. I forgot what that was called. If I would have forgot what water is called, you could probably laugh really hard. But this is hydrogen sulfide, right? And this is like water. It has some properties like water, except it's actually toxic and it stinks really bad. But it's also a Lewis base. It's got a pair of electrons. Ammonia and amines. We'll talk about amines in a bit, but like nitrogen, three things, lone pair, Lewis base. Phosphorus hydride is also, it's got a pair of electrons. And then also like a halogen, Cl minus, Br minus. All of those are Lewis bases. Lewis bases donate or share their electron pair with a Lewis acid to form a covalent bond. Here's an easy one. H plus reacts with water. So remember also, I'd circle this lone pair too. I'd circle the O minus and have it go attack the proton. These are chemical reactions. This is a very simple chemical reaction of A plus B makes C, right? And what about aluminum trichloride reacting with trimethylamine? Well, it also is a Lewis acid base reaction. Probably circle the lone pair, attack chlorine. And now you have a Lewis acid base complex between nitrogen and aluminum. You should be able to double check if the charges are correct, right? With the dots minus dashes rule. But yeah, of course, it makes sense that if we're adding electrons, we have neutral plus neutral, I'm giving electrons from the right thing to the left thing, that maybe it would become negatively charged, right? Yeah, cool. So an arrow is just drawn from the electron density towards the electron deficiency. That's a general rule. We always go from density towards deficiency, just like we do in resonance structures, and usually draw a circle. It really just helps you when you're keeping track of your electrons. If you got a lone pair, circle it first. Another example, boron trifluoride reacts with diethyl ether, and the lone pair of ethyl ether would react directly with boron, and it forms a complex, okay? And this just shows kind of like how the two molecules attach in three-dimensional space. Okay, so now we're moving into even more organic chemistry, nucleophiles and electrophiles. This is kind of like Lewis acids and bases. Okay, so nucleophiles and electrophiles are complementary to the concept of Lewis bases and acids, and are used to describe a gazillion chemical reactions all the way through organic too. So we got to get really comfortable with nucleophiles and electrophiles. Even though, you know, we're not going to see them extensively until a couple chapters, but I'll show an example now. And actually, the Wikipedia definition of nucleophile is really good, so we're going to use that. In chemistry, a nucleophile, literally a nucleus lover, phile for lover, is a reagent that forms a chemical bond to its reaction partner, the electrophile. So the nucleophile attacks the electrophile by donating a pair of bonding electrons, okay? Because nucleophiles donate electrons, they are by definition Lewis bases. So nucleophiles are Lewis bases. All molecules or ions with a pair of electrons can act as a nucleophile. That's a simple definition of a nucleophile, okay? Need a pair of electrons. Definition of electrophile from Wikipedia. In chemistry, an electrophile, literally an electron lover, is a reagent attracted to electrons that participates in a chemical reaction by accepting the electron pair in order to bond to the nucleophile. Because electrophiles accept electrons, they are Lewis acids. So electrophiles are Lewis acids. Most electrophiles are positively charged or have an atom which carries a partial positive charge. So we call that delta plus, right? Delta plus for partial positive. Or have an atom which does not have an octet. So that could be like BH3, we just said, or BCl3, carbocations, right? They do not have a full octet. Both of these reactions are between a nucleophile and an electrophile. I'll draw one out on my paper with my webcam in a second, but these are pretty simple. These are nucleophile reactions of nucleophile, left thing, electrophile, right thing, okay? So OH minus can attack chloromethane to form methanol and chloride. This is your next newest organic reaction. Now this we will learn extensively in chapter 6, I think. So don't worry too much about this, but right now this is a major class of chemical reactions in organic chemistry. What's this delta plus, delta minus thing? Very, very helpful to draw this. Delta minus is a partial negative charge. Chloride is electronegative. It is partially negative. So what happens to carbon? It becomes partially positive. So usually definitely when you're learning these things, drawing those delta negative, delta positive really helps you to understand the electronics. Okay, another one, hydroxide, same nucleophile, can attack HCl, which is also delta plus, delta minus, to form water and Cl minus. So these are chemical reactions, right? Note the direction of the arrows, note the partial charges. I usually draw delta minus, delta plus. Certainly when I'm introducing this to you guys, we will do that. You identified the nucleophiles and electrophiles? Well, we just did. Nucleophiles on the left, electrophiles on the right, okay? Sometimes in this case, I call the electrophile a substrate too. We'll see that word again, substrate. The first reaction is called nucleophilic substitution. This is chapter 6, I think. Yeah, or something. This will be an entire chapter on essentially this reaction. The second reaction, as you've seen many times before, is an acid-base reaction. It's not that exciting. This is kind of Gen Chem-ish. The distinction is a little confusing. We'll address it more later. All right? So nucleophilic substitution, the general class of reactions of haloalkanes. A haloalkane is the thing with a halogen, chlorine, bromine, iodine. They're also called alkyl halides. We'll cover that extensively in chapter 6 and 7. More examples. This is a molecule with 4 carbons and a Br and an I minus. It forms this product. And what about this one? It's 2 carbons, iodine, and NH3, which is also a nucleophile. So iodide and NH3 are both nucleophiles. And that forms this product. So we're going to show these on the webcam. Before we do that, a CX bond constitutes a functional group. So this thing is going to be called a functional group. We'll talk about functional groups in a second. Haloalkane. It just means a pattern of atoms that we see. Also, the iodoethane is a functional group. It's the center of chemical reactivity, and these are called haloalkanes. Let's draw the arrows. So I'm going to switch to my other webcam. All right. So somebody tell me, well, I'm going to try to involve you guys. What is the first thing I should do? For I minus, what should I do? Anybody know? Because it looks like iodide is going to be the nucleophile or electrophile. You guesses? I can't see chat. So if you're chatting, I can't see anything. Let's see chat. Well, now we see it. Okay. All right. Cool. So somebody said something file.
A nucleophile.
Nucleophile. Got it. So the first thing I would do is draw the lone pairs. Draw all of them. There's 4 of them, right? 1, 2, 3, 4. Usually, I'll redraw it up here. I'll put the minus there. Okay, that's maybe a better way to draw it. All right. Okay. Second thing I do. This is using the hints that I recommend to you guys. Draw some sort of shape, like a circle on the nucleophilic lone pair. Pick a lone pair, and it's going to be the nucleophilic lone pair. Okay, and now as we just learned, there's 2 arrows from the nucleophile to the electrophile. One is to form a bond. The other is to break a bond. So the iodide attacks the carbon to form a bond. Can't stop there though, because I need to have 10 bonds on carbon, or 5 bonds on carbon, which would be pentavalent carbon, right? Pentavalent carbon is never, never, never good. So you can't have 5 bonds on carbon. So we break a bond, okay? All right, so that's the full reaction. We also call this a mechanism. Mechanism arrow. So a lot of your organic chemistry is going to be learning these mechanism arrows. This is not a complicated mechanism. But in organic 2, you're going to have like complicated 20-step mechanisms, and you're going to have to know them. So it's good to start with the easy stuff, right? So this is a nucleophilic substitution reaction. I minus attacks, kicks off Br. You get this. Yeah. Cool. I like to actually put the arrow, let's be very specific, and put it really onto the BR, right? Cool. What about this one? Now we drew the lone pair for you. It looks like the nitrogen is attacking the carbon, kicking off iodine. So the lone pair is already there. Circle the lone pair, attack the carbon, which will kick off the iodine. You know, normally I'd have a line to I, and I'd break from the line to the I, just like I did up here. Can't really do that here, so I'm just gonna do this. It's a little sloppy, it's okay. All right, and then we clearly make I minus, okay. Now, there's just another name of these things. The Br and the iodide are called leaving groups because they left. Leaving group, Lg. So the leaving group is the thing that left, right? So we're going to get back into leaving groups and SN2, or sorry, nucleophilic substitution, chapter 6. Yeah. Okay, back to my sharing. Cool. All right, so we just did a real mechanism of a chemical reaction. 2 reactions, nucleophilic substitution reactions, right? Okay. Functional groups. Now we're going to take a little detour from chemical reactivity to kind of like the more structure of molecules and this idea of functional groups. We just said what functional group is. It's a arrangement of atoms that maybe have a specific chemical reactivity. So functional groups are specific arrangements of atoms found in molecules. They define their reactivity as a whole, with polar functional groups typically possessing the most interesting reactivity. Definitely going to see that the polar functional groups, like with an oxygen or a chlorine or something, are the most reactive. The majority of this textbook, after about chapter 5, is let's talk about a functional group. Let's talk about another functional group. Let's talk about another functional group. And we just, and the more you know of these functional groups, the more you just know of organic chemistry, the different reactivity of them all. Okay, first one, hydrocarbons are a class of molecules that contains only the elements of CH. The most boring functional group on the planet is just methane, ethane. It's almost so silly that we don't even, like it's arguable, is it even a functional group? Because it's, usually it's like you need an atom, like a chlorine or a bromine or an oxygen to be a legitimate functional group. So this is kind of arguable, like, is it really a functional group? I don't know. But hydrocarbons contain CNH. There's several classes: alkanes, alkenes, alkynes. We already talked about those. Aromatic, so benzenes and stuff. Also cycloalkanes. What do you think that is? It's a alkane with a ring, like a cyclic alkane. Alkanes are simple molecules composed of CC single bonds. Methane, ethane, propane, and butane. And you're going to get practice learning the names of these, and then all the way up to 10 carbons. We also have cycloalkanes that contain a ring. So cyclopropane and cyclobutane are examples of cycloalkanes. Alkanes are not polar and are typically kind of not reactive, right? I said they're kind of boring in terms of reactivity. They are not very reactive comparatively to polar molecules. Alkenes and alkynes contain a CC double bond or triple bond. We already know that. So these are, we have 2 alkenes and 2 alkynes. Ethene and propene are 2-carbon alkene and 3-carbon alkene. Ethyne, which is also called acetylene, is a 2-carbon alkyne with triple bond. Propyne is a 3-carbon alkyne. Okay, now these are what we call common names. So memorizing these kind of names is not really critical at all. And in this kind of open note class, memorization is not really going to be that big of a deal anyway. But these are like kind of, you're going to see like these kind of names, we call them common names. We also will see systematic names. Systematic names, there's a little more skill, and we're going to learn the skill behind systematic naming, starting maybe today. Aromatic are cyclic and typically contain alternating single and double bonds. So benzene, that's benzene. We've seen benzene already. Methylbenzene is a benzene with a methyl group, a CH3. It's also called toluene. And benzene is actually very carcinogenic, and so it causes cancer, and it's actually about 20% of gasoline. So be careful when you're pumping your gas to not inhale large amounts of gasoline, because you will. Well, the whole story, just because it causes cancer doesn't necessarily mean you're going to get cancer, but it's kind of the dosage and frequency and a lot of other parameters. But benzene is definitely a carcinogen. It causes cancer. Haloalkanes, we already talked about them. It's the functional group of Rx. R means a carbon fragment. X means a halogen, chlorine, bromine, iodine, fluorine. So bromoethane, chloromethane, and this is called halothane. It's a general anesthetic. It's a gaseous type thing, and it's on the World Health Organization essential drug list. So if you look that up on Wikipedia, there's like hundreds of drugs that are so common and very usually inexpensive that they're used like in every country. And this is one of them. It's actually a good general anesthetic, as a gaseous thing you would inhale. Alcohols, next functional group, ROH. That means carbon and then oxygen and hydrogen. This is a very important class of organic molecules. I think it's chapter 9, big chapter about the reactivity and properties of alcohols we'll get to. So ethanol or ethyl alcohol is 2 carbons OH. Methyl alcohol or methanol, it's a 1 carbon OH. These are common industrial alcohols. If you're in the days of COVID-19, you're probably putting a lot of ethanol on your hands with disinfectants. Most of the disinfectants either contain ethanol or methyl alcohol, or isopropyl alcohol is another kind of alcohol. Ether, ROR. So what does that mean, ROR? It means you have something on the left, oxygen, something on the right. So diethyl ether, sometimes we just call it ether. That's right, because it's so common that we often forget about these things are called ethyl groups. And the naming of ethers is really a later topic, but I'm just giving examples. Diethyl ether. But it's such a common ether that's used industrially by the ton that we often just omit the diethyl and it's called ether. So if somebody's in the lab and says, hey, can you give me some ether? You're like, oh yeah, diethyl ether, right? Tetrahydrofuran, or THF, is weird. It's a 5-member ring molecule, but it's got an oxygen in it. So it's, and this is called THF for reasons I'll get to later. But so THF is another very popular ether that's used in organic chemistry like crazy. I don't know, maybe I'm just old, but when I was young, everybody watched Back to the Future. And you might at least be familiar with some of the scenes from this movie of the little fire trails with the cars. That's diethyl ether. It is extremely flammable. It's extremely flammable. It makes little fire trails, and you have to be very careful with diethyl ether in the laboratory. One funny story about it is it's actually anesthetic, and it was used in early dentistry. So you're getting your tooth pulled, and you get a rag of diethyl ether to give you anesthesia. And then, of course, the dentist is smoking, because everybody used to smoke in their surgical rooms, and then catch the whole floor on fire. So diethyl ether is very flammable, and you have to be very careful with it in the laboratory. Work in a fume hood and stuff like that. Amines. Okay, so amines are generally some R group, like carbon with like NH2, or you could have 2 R groups in the NH, or 3 R groups in the N. Those are all different types of amines. Amine is just really a nitrogen-containing molecule and an alkane. Methylamine, CH3NH2. Dimethylamine, we have 2 methyl groups. Trimethylamine, so these are all examples of amines, and there's another whole chapter on amines that you'll learn in late organic too. This is also, I'm old. Blinky, the 3-eyed fish from The Simpsons. So if you watch The Simpsons, you may be familiar with this crazy mutated fish from one of the episodes. Thiols are kind of like an alcohol, but it's SH, right? Alcohol is ROH, thiol is RSH. Butane thiol. Butane thiol is 4 carbons SH. Okay, what's the difference between a thiol and a sulfide? A sulfide is RSR. It's kind of like an ether, but with sulfur, right? So this is dimethyl sulfide. It's carbon, sulfur, carbon. And I'm also old and remember it was one of the characters on Bugs Bunny. Pepe Le Pew, the French skunk. Anyway, so yeah, thiols are, they stink. They're also found in small quantities in things like garlic and onion that give you some of the flavors in garlic and onion. But also like if like a skunk actually uses them as a chemical defense mechanism. They squirt these thiols on you that are really nasty. That's kind of the smell of a skunk. Carbonyls. Okay, so now moving on. C double bond O. So the carbonyls are things that have a C double bond O on them. There's a couple types of them. These let's go through them. First one is C double bond O with 2 carbons on both sides. C double bond O with 2 carbons on both sides. This is called a ketone. And a typical example is acetone. So this is like a nail polish remover, industrial solvent. Ketone, okay? An aldehyde is kind of like a ketone. An aldehyde is C double bond O with 1 carbon and 1 H. 1 carbon, 1 H. So what's the difference between a ketone and an aldehyde? The aldehyde has a CH, okay? An acetic acid the top name is like the name of the molecule. The bottom is the name of the functional group. So this is a carboxylic acid, and that is a C double bond O, carbon on one side, OH on the other. It's a type of functional group, carboxylic acid. And this specific molecule is called acetic acid, which is vinegar, right? So you have vinegar in oil salad dressing, you're consuming small amounts of acetic acid. It's actually an okay flavor for foods, okay? Formaldehyde is the smallest possible aldehyde. So formaldehyde is C double bond O, HH. And it's used in a lot of purposes, actually like a preservative in biology. Formic acid is the smallest carboxylic acid. And this is C double bond O and an H on one side, OH on the other. So it's still a carboxylic acid, and this is still an aldehyde, but these are like special cases. They're like separated. Formic acid is also the poison that red ants use when they bite you and make your hand sting. Additional carbonyl functional groups. An ester. What is an ester? An ester is a C double bond O, carbon on one side, oxygen on the other, just like a carboxylic acid, right? Except now you have a carbon instead of a hydrogen. So that's called an ester. So this is an example of an ester, okay? And then we have amides. An amide is another carbonyl. All the carbonyls are C double bond O, right? Amide is a C double bond O, and then you have a carbon on one side, nitrogen with 1 or more or 0 things on it. So even if it's NH2, it's still an amide. These are examples of an amide functional group. And there's one more thing, a nitrile. A nitrile is C triple bond N with a carbon on it. So this is kind of a weird thing, but people consider it like a carbonyl. Instead of C double bond O, you have C triple bond N, and it has some of the reactivity of carbonyls. Okay, this is a cool summary, and you know, if you have a printer, certain sheets might be useful to print and put in your notes or something. Functional group name summary. So alkanes, alkenes, alkynes, aromatic rings. That's those. Then we have amines, carbon with nitrogen, alcohols and ethers, thiols, sulfides, and disulfides. So a thiol is SH. A sulfide is like carbon, sulfur, carbon. A disulfide is carbon, sulfur, sulfur, carbon. And they all have interesting uses. And these are actually a big component of protein structure. So if you're taking biology or biochemistry later, you'll hear about disulfides that rigidify proteins. Haloalkanes are carbons with halogen on them. Then we got all the carbonyls. Aldehyde, ketone, carboxylic acid, ester, amide, okay? Those are pretty much all of them. Nitrile, we mentioned that, is C triple bond N, okay? Now at some point when we're doing these quizzes, I'm gonna say, hey, identify the functional groups in this molecule. And you're gonna be like, oh, that looks like an amine. Oh, that looks like a ketone, you know? So you're gonna identify the functional groups. Now it becomes really easy given that I give it to you. So like on a real exam, it's a little harder because you have to memorize these. Not too much memorization in this course. Anyway, but this is a good summary of the functional groups. Okay, straight chain, branched, and cyclic alkanes. The different kinds of alkanes. You might imagine what a straight chain alkane is. It's going to be some carbons in a row. Branched means there's a branching point, and cyclic means it's a cyclic alkane. So these are examples. Butane. 2-methylpropane is, it's actually 4 carbons, 1, 2, 3, 4. This is a branched alkane, so it's got it's still 4 carbons, but it is an isomer. It's a constitutional isomer of butane. And so it's just a rearrangement. And we just put all 3 CH3 groups on a single carbon. Notice the molecular formulas too. It's 2 times the number of carbons plus 2. It's CX, H, 2X plus 2, right? C4H10, C4H10, right? Cyclic alkanes, though, are C4H2X, or CX, H2X, right? CX, H2X. So cyclobutane is, it has 2 fewer carbons, hydrogens, 2 fewer hydrogens. First 2 are called constitutional or structural isomers. We already talked about that term. You'll see it a bunch more. General formula, straight chain, we already said, is like C, X, or N, or whatever. CN, H, 2N plus 2. Cyclic are CN, H2N, okay? So it's going to be an interesting slight difference in the molecular formulas. Okay, so these are constitutional isomers. Butane, that's cyclobutane. With more carbon atoms, there becomes more possibilities of constitutional isomers. So imagine like 5 carbons. And like with 5 carbons, now we have 2 different constitutional isomers, right? Because we can just rearrange the atoms in different manners. Sometimes it's really easy to do this with skeletal drawings. Like you do a 5-carbon zigzag, and then here it's like, it's a 3-carbon zigzag with 2 lines on the end, and then here it's like, you could draw this in a zigzag skeletal structure, right? Skeletal. So it's easier to draw these kind of things in skeletal format. Okay, so as you add more carbons, n equals 1, 2, 3, 4, 5, 6, 7, it's 20, you can see the number of isomers grows really rapidly. So like a 20 carbon molecule has 366 thousand isomeric alkenes. So yes, I mean, like, as you can imagine, the molecules get more complicated. The more atoms, of course, the more combinations of, the bonding, right? Okay, naming. This is getting into fun stuff. One of the fun things you probably have not learned much about in Gen Chem, definitely not. Okay, given the diversity of possible organic structures, it quickly became obvious that we need a systematic nomenclature system. The standard system was developed in 1892, so a couple weeks ago, in Switzerland, and has been revised by IUPAC, which is the International Union of Pure and Applied Chemistry. It's like a major organization of chemists in the world, and it's been revised a bunch. But the basic idea was actually discovered in the 1800s, late 1800s. The basic format is substituents and then name. Okay, so we're going to go through these now. Substituents is usually going to be something that is attached to the chain. It could be a chlorine or something, right? The name of the parent chain will be like propane or something like that. Okay, so let's do some examples. 1-bromopropane. So usually with the way I interpret these, I go from right to left. I think about propane, I think about 1-bromo. How many carbons is on propane? You guys know that. I can't see chat, so you guys all know. Say it. Somebody say it. 3. Yes. Okay. So what do you think this means? 1-bromopropane. Maybe it's 3 carbons with a bromine on carbon number 1. That's condensed. Actually, condensed would be no lines. But skeletal. We love skeletal, right? So that's 1 bromopropane. 2-chlorobutane, what do you think? It's 4 carbons on butane, the chlorine's on number 2. There we go. Kekuli shows all the lines, but we really love skeletal. So yeah, there we go. So far so good. These are your first IUPAC naming examples. Recall methane, ethane, propane, and butane, okay? 1 bromo, 2-chloropropane. Well, start from the right, we see propane. What I would do is draw propane, 3 carbons, 2 lines as a zigzag. And also note how the substituents are alphabetized. B becomes before C. It has nothing to do with the position. It's the alphabetization. B becomes before C, right? Of course, that's, there we go. Propane, bromochloropropane, right? We cool? I think we're all cool. All right, okay, and now what? Okay, 1,4-difluorobutane. Guesses? That's butane with a fluorine on 1 and a fluorine on 4. That's not that hard, right? Now let's go the other way. It gets harder when you go the other way, right? Okay, and so first of all, what I do is I figure out the carbon chain. How long is it? 1, 2, 3, 4. Okay, so it's something butane, right? Something butane. But remember, there's something about the alphabetization. So, and oh yeah, number from the end closest to the first substituent. So do we number right to left or left to right? Looks like left to right. We go from the left, so there'll be 1, 2, 3, 4. But remember what we did up top, we presented the substituents in alphabetical order. So it's gonna be 2-chloro, we start with the Cl, 2-chloro, 1-fluoro, 2-chloro, 1-fluoro, butane, 2-chloro, 1-fluoro, butane, 2-chloro, 1-fluoro, butane. And it helps to draw some numbers in, right? It's not 1-fluoro, 2-chloro, because it's silly rules. Alphabetization is a silly rule, but you're gonna have to learn that as silly rules. And that's one of the first silly rules in this course, I think, that you have to learn. Okay, so I usually recommend students remember 1 through 10. 11 and 12 are just kind of weird names, but it goes methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane is 9, 10 is decane. If you're like challenging yourself, you can do 11 and 12, or undecane and dodecane. I'm not going to ask those in class, okay? But also, I mean, everything's open notes. I could, which shouldn't be a big deal, right? You have a table now. It's in your notes. Okay, now if you're really like challenging yourself, you can memorize up to 20. From 13, it's tridecane, 14 is tetradecane, pentadecane, hexadecane, heptadecane, etc. So I don't know any organic chemists that know these ones to memory. The boiling points increase because the more carbons, the more interactions, or like the van der Waals interactions between molecules. Melting points also increase because there's more interactions between the molecules as you get more atoms. The density also increases too. There's a trend that they just all could increase. Okay, let's do this one. We're just gonna step through it logically. And the rules are, you can follow these little instructions, and it helps you. Find the longest chain and name it. Find the longest chain, what is it? Somebody say it. 1, 2, 3, 4, 5, 6, 7. 7, so it's what?
Heptane?
Heptane, yeah. We number left to right or right to left?
Left to right. Left to right.
Left to right, yeah. And closest to the first substituent. So your name is going to be something heptane, right? Something heptane. Identify all the groups and attached, and there's substituents. What I usually do on my paper is I'll write heptane, and then I'll kind of write out the substituents. And if you have an eraser, it really helps because you might have to reorganize them all. I usually do the name, and then I list the substituents kind of vertically even, like 2-bromo, 4 chloro and 5 fluoro, right? 2 bromo, 4 chloro, 5 fluoro. And then I'll rearrange them with my eraser and get them alphabetically, right? So number the carbons closest to the end of the first substituent. So we know it's 1, 2, 3, 4, 5, 6, 7. If two substituents are equal distance, we use the first letter of the alphabet to decide which substituent wins, okay? Right here, it's very clear that it's left to right. And we'll write the name. So it looks like it's going to be something heptane. It looks like with my magical ability to alphabetize things in my brain, it looks like it's going to be 2 bromo, 4 chloro, 5 fluoro. 2 bromo, 4 chloro, 5 fluoro, heptane, right? This will definitely be something you're going to see on some quizzes coming up. There's a lot of practice in the book too, so I practice. Okay, how about this? Start with a long chain. How many carbons? 1, 2, 3, 4, 5, 6, 7, 8 is what?
Octane.
Octane, yeah. And so what about when we have multiple fluorines? Well, it's not going to be like 1 fluoro, 1 fluoro, 3 fluoro, 4 fluoro. Organic chemists are efficient. I think it was created in Germany, and Germans love efficiency. And so yeah, it's going to be 1, 1, 3, 4 tetrafluoro. So we just name all the fluorines are tetrafluoro. 1, 1, 3, 4 tetrafluoro. There's our numbering. 1, 1, 3, 4 tetrafluorooctane. 1, 1, 3, 4 tetrafluorooctane. Okay. How about 1, 7 dibromo, 2 chloroheptane? Let's draw that guy out. So how many carbons? And heptane is 7, right? So we started with a 7 carbon zigzag. Well, can we not give it away? 7 carbon zigzag, and it looks like we have a bromine on 1 and 7 and a chlorine on 2. So it's actually really easy to draw. So start with a zigzag, skeletal structure, bromines on 1 and 7 and chlorine on 2, all right? Now this is a second silly rule of this course, maybe. I don't know if I did any other silly rules, but this is a silly rule for naming. Notice how we alphabetize. It's by the B and the C, okay? The di, we don't alphabetize by the D. We alphabetize by the bromine. So it's 1, 7 dibromo, 2 chloroheptane. Okay, and I actually like the little arrows to remind yourself, that where do I alphabetize by? Even up here, I'd probably put a little arrow under the F, and it's like, oh yeah, that's the F that I would alphabetize by, even though you don't have to alphabetize anything here. It's just useful, okay? Right. Okay, how about this weird example? So it's, what's the longest chain? So it's 7, so it's heptane, right? How do we name it if there's apparently a CH3 on carbon 3? Well, what would, okay, what would this substituent be if it was its own molecule? It would be like a single carbon with 4 H's on it. It would be methane, right? Methane. But when you have this as a substituent, it's not like 3 methane heptane. That sounds silly, right? It's 3 methyl. So when we have something like a single carbon that's attached as a substituent, we call it, we use like methyl, or it could be like ethyl or propyl. Like those are how you name a substituent. This is a substituent on carbon 3. So the name is going to be 3-methyl heptane. 3-methyl heptane. IUPAC says this is a heptane with a 1 carbon alkyl substituent at 3, and we call that methyl. We name it, so it's rather than like blah 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 ane, it becomes blah 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 YL. So methane becomes methyl. That's how we name a substituent. That's the name of it, is 3-methyl heptane. Okay. Now, step further. This is where a lot of people freak out because this gets a little more complicated, but we got to get through this. There's these things called branched alkyl substituents, and there's a couple examples here. Isopropyl, which is propyl. How many carbons are propyl? It's 3, right? Isopropyl is a 3-carbon alkyl substituent with branching on the middle carbon. Okay. Isobutyl is the same exact thing, except there's 4 carbons and you just have an extra CH2. So look at the relationship between isobutyl and isopropyl. What's the difference? You just have an extra CH2, right? Sec-butyl is yet another one where you have 4 carbons and you attach off the second carbon. So sec-butyl. Sec-butyl is another butyl. We have a couple butyls. We have isobutyl, we have sec-butyl. What about this weird one? Tert-butyl. It's yet another one where we have carbon and 3 CH3s on it. And then neopentyl is one more. It's the same thing as tert-butyl with an extra CH2 on it. So these are weird, right? It's a little weird. You're going to get used to seeing these. You've probably, I imagine, especially with COVID-19, heard of isopropyl alcohol, right? What do you think the structure of isopropyl alcohol is? It's 3 carbons. You have an OH at the squiggly line. The squiggly line just means, you know, where something's attached. Isopropyl alcohol is 3 carbons with an OH on the middle one. What do you think isobutyl alcohol would be? It'd be this with an OH on that CH2, right? Isobutyl alcohol, okay? Sec-butyl bromide, what do you think that would be? That would be sec-butyl with like a bromine where the squiggly line is, okay? Tert-butyl alcohol is a very popular alcohol, and it's tert-butyl with an OH right there. So 4 carbons, branched like this, and then OH. And then neopentyl is a kind of weird one, not as popular, but it's easy to see neopentyl relative to tert-butyl. It's the same thing as tert-butyl, but it's got an extra CH2, right? Okay. Let's name this weird guy. Let's name this one. And we're going to use those funny names we just learned. So what's the length of the parent chain? It's 1, 2, 3, 4, 5, 6, 7, 8, 9. What is that? It's something name. 9 is?
Nonane?
Nonane. Nonane. Do we number left to right or right to left?
Left to right.
Yep. 1, 2, 3, 4 bromo, 5 something, 5 something, nonane, right? It's 4 bromo, 5 something, nonane. Okay. There's our numbering, 4 bromo, 5 something, nonane. But we just learned this one. It's a 3 carbon piece, right? Something propyl. It's like alcohol. It's,
Isopropyl?
yep. 4 bromo, 5 isopropyl, nonane. That's the name. 4 bromo, 5 isopropyl, nonane. Okay. Funny alphabetization trivia. We go by the B, and for isopropyl, we go by the I. Okay. It's not by the P. So the alphabetization rules are usually a source of panic as you start learning this. It gets a little crazier, and we'll get through it. But just be ready for it, but it's going to be a little painful. With practice, it just comes naturally, though. But yeah, it's B and I. Okay, 4 bromo, 5 isopropyl, nonane. Now this is going to be this is another source of panic. So we're going to be panicking a lot in the next 15 minutes. Okay, and don't worry. This is always a source of panic every time. Here's another way to draw isopropyl. We have isopropyl, yeah. This is easy. This is doable. If you know what an isopropyl is, you will memorize those silly ones. And let's go back to slide. The only way to know these is memorization. This is one to print out and add to something just to practice a couple times. You just have to memorize these. There's no way to really like systematically figure these out. I just memorize them. I print this out and just look at it for a while and it'll just come to you. All right, so we got this. This is doable, yeah? Okay, isopropyl can also be considered something called a complex substituent, and we can name this systematically. So let's think about this. If I just look at the isopropyl group, it's this little thing in the brackets, right? That's an isopropyl group. And I want to name the isopropyl group systematically itself, because sometimes we use the word isopropyl, but sometimes we want to show it as its own like little fragment that we name systematically. So what I'm doing here is I'm numbering carbons 1 and 2 off, it's part of the isopropyl group. It's carbons 1 and 2. And on carbon 1 is a what? A CH3. What's a CH3 called? A methyl group, right? So this thing can be called isopropyl, 5-isopropyl nonane. But we can also call it a 1-methyl ethyl. This is because it's an ethyl. That is a 2-carbon piece with a methyl on carbon 1. We renumber from carbon 1, carbon 2, right? It's carbon 1, that's carbon 2. It's this, another alternate name of this is called a 1-methyl ethyl substituent. And that's scary, and I know those students usually hate this. I can't see people's faces if they're smiling or frowning right now. Usually everybody's frowning right now, okay? So it'll be okay, we're gonna get through this. But this is an alternate way of representing isopropyl. It's a 1-methyl ethyl substituent. Okay, and the alphabetization, so this is an alternate name. These are the same exact molecule, 4-bromo, 5-isopropyl nonane, or 4-bromo, 5, in parentheses, 1-methyl ethyl nonane. These are identical, and yes, you have to know them both. So we'll get through it, and if you have a couple of questions, they'll be clarified as we proceed a little bit, all right? So, and notice the alphabetization rules. We go off the B, we go off the I, we go off the B, we go off the M, okay? All right. The branch substituent is identified either using the common name, which is the top one, isopropyl, and all the ones we just saw on the last slide, or a complex substituent. So this is called a complex substituent name, all right? Okay, let's go crazy. If you aren't crazy enough. All right, so first thing we're gonna do, let's name this. We have a couple ways to name it. All right, so first thing, what's the length of the parent chain? So we're looking for the longest chain, and it looks like it goes horizontally. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's easy, right? What is it? It's nonane, right? Nonane. Okay, so we're halfway there. We got our nonane, right? There we go, nonane. Then we just have to figure out the substituents, right? So it looks like on carbon 5 and 3, we have to number from right to left because it's closest to the first substituent, right? We're cool so far. What are the easy ones? Looks like we have a methyl on 4 and a methyl on 5, right? That's easy. And then we also have this weird thing on 4. What did we call that weird thing? It's on your table. It's one of the butyls.
A tert butyl?
You got it. Tert butyl. That's a tert butyl group. Yep. Okay, we got our substituents. Now we have a name, right? So it's 4 tert. Oh yeah, and here the alphabetization. And we'll review all the alphabetization in a bit. But we don't go by the T. We actually go by the B. Okay. 4,5 dimethyl, and we still go by the M here. So this is actually a reasonable name. 4 tert butyl, 4,5 dimethyl nonane. Okay. Now let's think about the other way to name it, because there's another way we can name this thing, right? The tert butyl, we have 2 ways we can name it. Tert butyl, we know, but alternatively, we just look at it and we imagine it's a 2-carbon thing, a 2-carbon chain, carbon 1, carbon 2, right? With 2 things on carbon 1. What are the 2 things on carbon 1? It's a something and a something. CH3s. It's something ethane. It's di something ethane. It's going to be 2 things. What are those 2 things? They're begin with M. Methyl. Dimethyl. It's actually dimethyl ethyl. So the alternate name for this is going to be dimethyl ethyl. 1 dimethyl ethyl. Because if we consider this an isolated fragment, right? There's the ethyl. We have 2 methyls on carbon 1 and 2. Sorry, they're both on carbon 1, so it's dimethyl ethyl, right? Okay, so this is an alternate name for it, right? And you're gonna have practice, and this is gonna be, once we get through naming, and we're not that far from being done with naming of these, then it's time to practice, and you'll just kind of get this. First thing is And this is makes your head want to explode. Dimethyl-ethylnonane. We got that. 4,5-dimethyl-ethylnonane. Where do we alphabetize? Like when we say dimethyl, we already said that earlier. It's by the M, right? Okay, so now your head's going to explode because when we say dimethyl-ethyl, 4,1,1-dimethyl-ethyl, we actually alphabetize by the D. It's silly. I did not make up these rules, but when you have like substituents directly connected on a chain, like dimethylnonane or dibromo-octane or something like that, you don't use the D, you use the first letter of the thing, right? All right. But when you have an complex substituent, it's always the first letter, okay? And I know you're gonna, once you see it all, you're gonna just practice a bit and it'll be, make sense, but this is a little weird at first, right? Silly rules, right? So we go by the D here and by the M there, all right? So that's what we got. How about this? Let's do this one. Okay, first thing you do, we always build a name right to left. So meaning we find the longest chain. Anybody know what it is?
Octane?
Oct. You got it. And now I was trying to trick you, but it didn't work. Because a lot of people will just say, oh, let's go left side to right side. And it looks like 1, 2, 3, 4, 5, 6, 7. And you're like, oh, it's heptane, right? It's not heptane. Actually, let me see. It is octane. You're correct. So you have to go down this thing. You have to be like 1, 2, 3, 4, 5, 6, 7, 8. It is octane, yeah. And don't make the silly mistake of like just going across, because that's wrong. You have to find the longest chain first, right? All right, so what do? There's our longest chain. And even though this looks like kind of like a tert-butyl, right? It kind of looks like a tert-butyl. It's not, though, because if we go through the longest chain, this is just a whole bunch of methyls on the chain, right? This is a trick question almost. It's really, there's no tert-butyls here. That looks like a tert-butyl, just like this is a tert-butyl, right? But this is not a tert-butyl. It's going to be 2,2,3,3,4 pentamethyl octane. It's 2,2,3,3,4 pentamethyl octane. 2,2,3,3,4 pentamethyl octane. So this was a trick. The trick was that you have to find the longest chain. You don't just start seeing tert-butyl and say, oh, it's something tert-butyl. No, it's not tert-butyl. You have to go through the longest chain, right? That's cool. Okay, so we're almost done with this. We're almost done with this. This just shows you all of those, the key ones. I'm skipping neopentyl, which was a little bit weird, and we're probably not going to see that for a while. But these are the key ones: isopropyl, isobutyl, sec-butyl, and tert-butyl. All right, these are the alphabetization rules. I. It's weird that sec-butyl and tert-butyl are both off the B. So the iso ones are by the I. It's just that the rule says that if it's something dash something, you go by the B. If it's something without a dash, like iso, then you go by the I. So it's weird, okay? All right, so now let's do the systematic names of these. 1-methyl-ethyl, we did that, right? Because it's like an ethyl with a methyl on number 1, right? Ethyl, there's an ethyl with a methyl on number 1. 1-methyl-ethyl. Alphabetization is a little weird because you go by the M. That's actually not weird. That makes sense. Go by the M, right? How about isobutyl? Somebody tell me. What's the chain? How many carbons is the chain? It's like 1, 2, 3. It's 3 carbons.
Propane.
Propane is correct, except it's a substituent. So it's actually propyl. It's propyl. But when there's a methyl on, is it carbon 1, 2, or 3? You have 3 carbons and a methyl on carbon number 2, right? There's a methyl on carbon 2. So it looks like it's going to be 2-methyl propyl, because there's the propyl, 3 carbons, 2-methyl propyl, okay? 2-methyl propyl. Okay, sec-butyl, what do you think? So I see also a propyl chain. Propyl, 1, 2, 3, right? There's your 3 carbon thing, propyl. And now we have a methyl on carbon 1, 2, or 3.
1.
1. It's 1-methyl propyl. Notice how isobutyl is called 2-methyl propyl. Sec-butyl, which is this funny name, is a 1-methyl propyl. So we have 1-methyl ethyl, 2-methyl propyl, and 1-methyl propyl, all corresponding to these different names, yeah? Okay, now this one. We already did this. We just did it last slide, right? It's like a ethyl with, looks like,
Excuse me.
how many methyls are on carbon 1?
I have that we did.
We just did this one last slide.
No, I mean the sec butyl one. I have a question about that one.
Yeah,
Why
yeah,
is it not butyl, and why is it methyl propyl? Why I can't?
Yeah, that's funny. Sec-butyl refers to, like, this is just a name given to this whole arrangement that contains 4 carbons, right? That's why it's butyl, right? But the systematic naming is, what we do is, rather than give this like its own little nickname, we're actually we're saying the same exact thing but systematically. So we say, oh, it's a propyl, 3 carbons, right? 1, 2, 3, with a methyl on number 1. So it's 1-methyl propyl, even though we use the word propyl, is identical to sec-butyl because they're both 4 carbons, right? Here it's 1 plus 3 is 4. Here it's just 4. Butyl is 4, right?
Okay, thank you.
So this is ethyl. Ethyl, 2 carbons, with 2 somethings on carbon 1. 2 methyls. It's dimethyl ethyl. We call it 1,1-dimethyl ethyl. 1,1-dimethyl ethyl, with the only weirdness being that alphabetization is a little funny because we do alphabetize off the D, right? We alphabetize off the D. We don't alphabetize off the M. If it's a complex substituent and we name it systematically, we alphabetize off the D, not the M, and that is weird. Because if I say 2,2-dibromooctane, right? 2,2-dibromooctane, you know, you alphabetize off the not the di, but the bromine, right? So, okay. So that's weird. It doesn't get weirder than this for the naming. I think we're yeah, we did a couple weird things, but the naming that's about as weird as it gets. So the rule summary: iso blah blah blah, alphabetize based on I. Chert blah blah blah, or sec blah blah blah, alphabetize off the X. Systematic names, you always alphabetize off the first letter. That's the rule, alphabetization rules. Okay. Couple practice: name these using common and systematic. This is great practice. Try this. I'm not going to do it for you. You can do these, or come to office hours. But let's just identify this one. Is it something butyl, right? It's which one is it? Something butyl. It's that one.
Chert.
Yeah, chert butyl. Or the other name for chert butyl is 1,1-dimethyl ethyl, right? So given that, you can name this. But with this weird one, which one is it? It's another butyl. 4 carbons. 1, 2, 3, 4. Which one is it? Is it isobutyl, sec-butyl, or chert butyl? It's a sec-butyl. It's a sec-butyl. Okay. I think we're basically out of time, but I think what I'll just end on this slide, which is definitely good practice. And if you want to practice this, and I really think right now, or tomorrow or something, is the time to get these things down. Draw these molecules and then provide an alternate name using common names. Common names are like isopropyl, sec-butyl, isobutyl. So try these names, draw them, and then give the alternate name, okay? And then the other thing to do is draw these ones, but then give a alternate name using systematic nomenclature. And that's the dimethyl ethyl, 2-methyl propyl, etc. If you can get through these, you got this down. And this is not that hard once you try it a couple times, all right? I think we are 1 minute over, so I'm going to stop the recording, and